Hello, my name is Adriane Chapman. I'm here with my colleague, Pamela Ugwudike. We are looking at how algorithms, not the data, can introduce biases into the world. When we started this project, the prevailing belief was biases are found in the data. Algorithms are not biased, they just work on biased data. In this work, we look at a classic predictive policing algorithm. The original creators developed the model by finding a mathematical model that fit the data they had from the local police. Versions of this algorithm are now employed by police forces around the world, and we've seen many cases that show it is biased. Over to you, Pam.
So we were motivated by the lack of clarity emerging from existing studies of predictive policing algorithms. We reviewed the relevant international literature. We found that studies in the field were producing mixed results. They were focusing mainly on the impact of data on predictions. Now, when we considered these findings, we felt that further research was required to understand conduits of bias and open up avenues for thinking about remedial strategies. So this provided the rationale for our study. So, when we considered existing findings, we felt, as I said, that further research was required to investigate whether, bias predictions could be traced solely to the type of data used for predictions, or whether there were other conduits of bias that could be linked to other aspects of model design, such as a theory of crime that influences how a model is designed. So our project aims to address several questions that would help us understand how bias can permeate a predictive policing algorithm. One of our main questions was, how does model design influence outputs? Now, to address this question, we explored whether and how aspects of model design, like the choice of data and the specific crime theory that developers select, can inject bias into its output. So we added a new dimension to the study of predictive policing algorithms. Unlike many studies in this field, we did not focus only on the impact of historical data on predictions. We also explored whether and how the specific theory that guides the design of an algorithm and the way it operates can affect its output by, for example, introducing bias. So we considered the impact of criminological theory on predictions. Now, when we say theory in this context, we mean anything from a formal grand theory to the basic assumptions, ideologies that inform how an algorithm is designed. The predictive policing model we studied relies on the near repeat thesis, which is the theory that holds that a crime incident would normally trigger a temporary increase in crime in nearby locations shortly after the initial incident if there are no measures like police patrols in place to detect or to deter potential offenders. Now, the near repeat thesis is generally based on the idea that crime events occur just like earthquakes that trigger a series of nearby aftershocks. So in our study, we investigated how this theory can influence output of the predictive algorithm we selected. We also investigated how another theoretical perspective in criminology known as positivism can impact on the predictions of the algorithm. Now, positivist perspective suggests that crime is a result or is a product of factors beyond the offender's control. It could be sociological factors, biological or psychological factors. Now, unlike the near repeat thesis, which depicts crime as a non-random event, positivist theories imply that crime can be random in the sense that it does not necessarily follow a specific temporal or geospatial pattern. Positivists believe that the best way to prevent crime is to address the sociological, psychological, and biological causes. So over to you, Age.
So we investigated whether and how the near repeat thesis, as embodied by current predictive policing algorithms, influences the outputs of the model. We want to understand whether the algorithm itself can introduce bias, in contrast to the accepted wisdom that algorithms cannot be biased, but data can be. To do so, we created a computational model that replicates the original algorithm used by police. We created several data sets synthetically. The first one mimics the near repeat thesis. Remember, the near repeat thesis says that crime is not random and is spatially and temporally related, and that a piece of crime will likely engender crime nearby. So for the first data set, we created a series of crime that follows this pattern. The second data set we created to mimic the positivist theory in which crime is effectively random. And for that, we geospatially and temporally placed crime randomly across the map. The third data set we created by looking at real crime data from Kent in the UK and created a data set that mimicked its distribution in temporal and spatial patterns. We then did an investigation around the crime reporting rate. Crime reporting rates are really important. Crime happens, but it is not always necessarily reported. We used multiple different methods to identify what a likely crime reporting rate could be. We looked at crimes reported to the police, drug-related mishaps reported to hospitals, as well as surveys about crime. The goal is to understand how often crime actually occurs and whether or not it has been reported to the police. From these, we identified background crime reporting rates across many different types of crime to be used in our model. From that point, we then seeded crime on the map. We took either our near repeat data set, our positive data set, or our real data sets, and took 5 days and set the crimes of each of these fake data sets seeded across the map. We then allowed the algorithm to run over about 40 days. From that, a very stark result comes out. What we're looking at here is on day 1 in both the near repeat and the alternative thesis. You can see that crime is effectively spread out and the police response to that crime is effectively spread as well. The clusters of yellow and purple dots in each graphs are one large cluster. There's no separation. So crime is occasionally reported and the police are dispatched accordingly. At the start, there's no separation. Now, the near repeat thesis, remember that we identify for this thesis, the crime is geospatially relevant and related. A crime in one area will indicate there's likely crime in the same area. And in fact, after 48 days, you can see that the police are being dispatched disproportionately to specific areas. And this makes sense for the near repeat thesis because crime is not random. And you can see that by the separation of the yellow and purple dots. The hard part here, the interesting part of this, is looking at day 48 of the alternative thesis. Remember, the alternative thesis is that crime is not random. Sorry, it is random. And indeed, the data in our data set we generated is random. It has no hotspots. But by day 48, we see the police are being dispatched to specific areas, and we have a separation occurring of where they're dispatched and where they are not being dispatched. In other words, the algorithm itself is introducing a biased feedback loop, even when the data itself is not biased. Basically, what's coming out here is that it's not only in addition to studies that have shown that there's bad data, we've shown in this work that the model itself, or the choice of model itself, has the potential of creating bias in random data.
So as H said, our study found evidence of runaway feedback loops, which means that the model we studied has self-reinforcing properties. Now, there are several adverse social implications that can arise from this, but I'll highlight a key implication, which is that a self-reinforcing predictive algorithm runs the risk of normalizing the labeling of affected areas as chronically high-risk locations. Now, this can trigger higher rates of police dispatch to such areas. And several studies already show that affected locations are typically the low-income areas that are mainly populated by minority communities that are already over-policed. Now, the extra police dispatch can reproduce their disadvantage by further exposing them to even more policing and higher rates of criminalization. Over to you, H.
As a small part of this work, we looked at the problem of how we got from an academically defined model around police data to the deployment worldwide of predictive policing systems, and what steps could have been put into place to prevent it or to modify it to mitigate its impact. There are a set of ethical tools available for the analysis of a system like this. Additionally, there are digital ethics committees. For example, in the UK, the police have an ethics committee to understand what tools are available and how they will impact their communities. However, these committees are not often as widely used or have the power that they need in order to make these wider decisions. In addition to that, there are many ethical frameworks and guidelines in existence about when to use algorithms or data. Unfortunately, in this case, there are 3 main problems. One is that the set of circumstances, there's only one algorithm, AlgoCare, which is completely voluntary to use. It is made for this particular scenario. Additionally, most of these guidelines do not actually address the needs of all of the stakeholders, from the producer to the consumer to the people buying and instantiating and acquiring these, to the voiceless people that it is being applied to. Finally, there are no regulatory requirements that require the ethical considerations or the use of these ethical guidelines before instantiating and using one of these tools. As I said, in this case, the use of AlgoCare ethical framework is completely voluntary. Our work is showing that in addition to the known problem of bad data, the model has the ability to create feedback loops and create bias even where none existed, and that there's a dearth of tools for stakeholders to use that represent all stakeholders and provide a real regulatory reason to apply them. I'd like to conclude by saying that this was the first work that looks at how algorithmic models themselves and the design choices that led to choosing the model can impact the biases and unfair deployment of these systems. Technologists are fond of saying algorithms cannot be biased. In this case, we've shown that algorithms incorrectly applied can indeed insert bias. In doing so, we created a framework that is open source and is available for any and all researchers to explore the impact of their choices. We explored on a very small population where we mimicked the near repeat hypothesis and a positivist hypothesis. The framework that we developed allows you to choose whatever type of data you would like to play with and substitute in your own model choice to test and run under different scenarios to see and understand the outcome of how police are deployed. That concludes our talk. Thank you for listening.
Thank you.